analyze f of x equals to sine x when a is equal to 0. Well, step one. In step one, we have to use the theorem and Maclaurin's inequality, Taylor's inequality. To prove that sine x is actually equal to the sum of its Taylor series. In this case, we're working with Maclaurin series, that's fine. So our theorem says if f of x can be written as the sum of Taylor series plus a remainder, and if, so remember that you're working with an interval of convergence, and if the limit of your remainder while n goes to infinity is equal to 0, for sure you can say that f of x is equal to the sum of its Taylor's series. Okay, to prove the theorem, we use Taylor's inequality. Taylor's inequality say that if the n plus 1 derivative of the function is less than or equals to n, when d is a positive number, then for sure you can say that the absolute value of the remainder is less than equals to n divided by n plus 1 factorial times x minus a to power n plus 1 over that. Okay, here we go. What do we have? We have function f, sine function. The n plus 1 derivative of your sine function is either sine or cosine, but we're lucky in this case. The absolute value of sine x is less than equals to 1, which is our m. Absolute value of cosine of x is less than equals to 1, which is equal to m and so. So no matter the derivative of your function, the higher derivative of your function, it's going to be bounded by a value like m, which in this case is 1. So what's the meaning of that? It means that your remainder is less than equals to 1 over n plus 1 factorial x minus a to power n plus 1. So when you take the limit of Rn, this limit for sure goes to 0. So we can use the theorem. So now that we can use our theorem, we can find Cn or the coefficients. So we know that sine x can be written as c sub 0, c sub 1x plus c sub 2x squared plus c sub 3x squared plus the rest of them. And c sub n is equal to the n derivative of function at 0 divided by n factorial. Let's find out. C sub 0 is equal to the zeroth derivative of sine, which is sine of 0 divided by 0 factorial. This gives you 0 over 1 or 0. C sub 1 is the derivative of sine, which is cosine at 0 divided by 1 factorial, 1 over 1 factorial, which is 1. C sub 2 is the derivative of cosine, which is negative sine. You have minus sine of 0 divided by 2 factorial, which is 0 divided by 2 factorial, or 0. Let us find C sub 3. C sub 3 is equal to the derivative of negative sine, which is minus cosine of 0 divided by 3 factorial. Here you get negative 1 over 3 factorial. Very well. It gets more interesting and interesting. C sub 4 is the derivative of negative cosine, which is negative sine. You get sine of 0 divided by 4 factorial, 0 over 4 factorial, which is 0. So note that when our values are even, we have even values, the Cn is equal to 0. Let us find C sub 5. C sub 5 is the derivative of sine, which is cosine. Cosine of 0 divided by 5 factorial, and we have 1 over 5 factorial. And we can continue this process. We expect C sub 6 to be 0, C sub 7 be negative 1 over 7 factorial, and the rest. So sine of x can be written as 0 plus 1 over 1 factorial times x plus 0 plus, here we have C sub 2, which is 0, and now we have C sub 3, negative 1 over 3 factorial, x cubed plus 0, and you have plus 1 over 5 factorial, x to the 5th plus 0, and then if you continue, you have negative 1 over 7 factorial, and the rest of the terms. So this is just the expanded form. This is your expanded. We're interested in writing this in compact form, like e to the x was equal to the sum x to the n over n factorial. We're going to write sine in compact form. So now let us write it in compact form. Sine x is equal to the sum. Note that here what you have. You have the sine plus minus. So I'm going to erase these. You have plus, you have minus, you have plus, the next term is negative 1 over 7 factorial x to the 7, and so on. So, and note that if you have even numbers, C sub n is equal to 0. Your negative sign shows that your negative 1 has an exponent. Sometimes it's positive, sometimes it's negative. So you have negative 1 raised to n. X is raised to odd exponents. So you have x raised to 2n plus 1 divided by your denominators are all odd numbers factorial. 2n plus 1 factorial. And n starts from 0, goes to infinity. This is our compact. So in the next step 2, you need to find R, the radius of convergence, by using the ratio test. The limit of, here you have negative 1 to power n plus 1, x raised to 2 times n plus 1 divided by 2 times n plus 1 factorial divided by negative 1 to power n, x raised to 2n plus 1 divided by 2n plus 1 factorial, while n goes to infinity. And this time must be less than 1. And in step 3, we need to find the interval of convergence. That's how we analyze the Taylor's expansion for our